Hello, this is the freshman tryout solution problem answers video. Um, so yeah, I'll just explain how to do these real quick because it was a pretty nice competition. So yeah, so first one, pretty self-explanatory, just 131. Everyone should have gotten this. Just 1 times 4 squared plus 3 times 4 to the first plus 1 times 4 to the 0th. That's just 16 plus 12 plus 1, which is 29. Okay, cool. Second one. It's just, you can just do the whole thing in base 3. That makes things pretty simple. So 1, 0, 0, 2, 1, 0, 2. Multiplying them, 2 times 2 in base 3 is, well, in base 10 it's 4. 4 in base 3 is 11, so carry over that 1. And then you have 0, 0, 0, 0. And then you have 1, 0, 0, 2. 1, 1, 2, 2, 0, 1 is your answer. Just doing the multiplication. You don't need the subscript, but like you can just add it. So yeah, that's the answer. Okay. Next one, this is where the actual math, I guess, comes in. Like, it's a lot harder. You have this problem. So let's kind of explain this. How would you do it in like base 10 terms? Well, you have 273. That's equal to, converting this in base 10, because we want the bases to be the same. You have d times b squared plus d times b plus d. So now you're like, okay, well, crap. I don't know what to do here. It's kind of hard. Like, I have 2 variables in one equation, and that's usually a nightmare. But if you notice, these all have d's. So what that means is you can factor out a d and turn it into this. And that's very exciting because we know that d is an integer, because that's just like the definition. B is an integer, b squared is an integer, b is an integer, and 1 is an integer. So both of these are integers, right? Now, why is that relevant? Because now we need to find 2 integers that multiply to 273. So first, let's take 273 and break it down into our prime factors. That should just be 3 and 91. Yes, 91. And then 91 breaks down into 7 and 13, which is exciting because now we know that d must be equal to either 1, 3, 7, or 13. Or some other combination of it. Actually, it shouldn't be. Okay, I'll explain why it can't be anything greater than this, or it shouldn't be, in a second. But yeah, like you could like say that as long as d is one factor, db squared plus b plus 1 will be another factor. Wait, yes, it should not be another factor. Okay, because yeah, d is less than b. So if d was, I guess we don't have an upper bound on b, but I'm assuming if we have this one as like, I don't know, what's the next factor that comes here? Like 39. B squared plus b plus 1 is definitely less than 39. Yeah, the solution for b would be less than 39, so that wouldn't work. Actually, I don't even think 13 should work, but I guess we'll get there in a second. But yeah, so if d is 1, then b squared plus b plus 1. Here we're just doing cases now. So yeah, that's equal to 273. So b squared plus b is equal to 272. This is a nasty quadratic. I mean, you can move it over and you'd probably be doing the same thing that I'm about to do. But what you can do is see that, hey, I need 2 integers such that when you multiply, there are 2 consecutive integers that when you multiply, you get to 272. So 272, that is a multiple of 4. So 68. Okay, that's also a multiple of 4. I'm just trying to get as close to like the center as possible. And wow, would you look at that? 4 times 4 times 17 is equal to this. But 4 times 4 is just 16. So therefore, b is equal to 16 as one solution to this quadratic. You could just get the same thing if you just took b squared plus b minus 272 and factored that quadratic. You'd get 16 in another solution. So b equals 16 is one solution. Now moving on to this one, if d is equal to 3, then b squared plus b plus 1 is equal to whatever is left over, which is just 91. So b times b plus 1 is equal to 90. This is a lot easier to see that, hey, 9 times 10 works. So b is equal to 9. Okay, cool. Now if d is 7, then b squared plus b plus 1 must equal 39, because 3 times 13. B times b plus 1 is equal to 38. There are no integers b that match that, because 38 is just 19 times 2, and those are only prime numbers, so that's bad. Now, I guess we can go to the last case, but it shouldn't work, because b squared plus b plus 1 must equal 21. So b times b plus 1 is equal to 20. So b is equal to 4, but since d is equal to 13, the condition that d is less than b is not satisfied, so this is wrong. So therefore, the only two things that work are 9 and 16. Okay, nice problem. So yeah, okay. All right. Next problem is, looks like it's using that one concept that I covered at practice once. Okay, so basically, okay, so say that the base 6 number has d digits. Actually, I don't like d. I'm just gonna use n, right? It has n digits. Then, and that's base 6. Then base 2 has 2n digits, right? But what does that mean in terms of number bases? Well, if the number has n digits in base 6, therefore it is in the interval 6. Say that's like number x. It would be 6 to the n minus 1 is less than or equal to x is less than 6 to the n, right? That's just like the number theory concept we covered. This is kind of an application of it's just an inequality that will always hold. And you might be wondering, well, didn't we do it if it's 6 to n is less than or equal to x is less than 6 to n plus 1, then has n plus 1 digits? Yes, these are the same thing, right? So, okay, back to, the reason they're the same thing is just because you're shifting that n by 1. Okay, 6 to the n minus 1 is less than or equal to x is less than or equal, or is less than 6n. Now, for the next one is 2 to the 2n minus 1 is less than or equal to x is less than or equal to 2 to the 2n. Now, x has the following range, and I don't know how 6 to the n and 2 to the n are related, so I'm just going to take the lowest of this inequality and the greatest of this inequality and just work with it, right? Because 2 to the base 2 number has more digits to the 6n, so therefore it's in the interval 6 to the n minus 1 is less than or equal to x is less than 2 to the 2n. But since I'm looking for an integer, we can just change this to 2 to the n minus 1 and then set that to a less than or equal to sign. Convince yourself why that's true for integers. But yeah, so now at this point, I don't really care what x is. I just need to find a n that satisfies this. So 6 to the n minus 1 is less than or equal to the 2 to the 2n minus 1. Now, let's literally just plug in numbers. If n is equal to 3, then we have 36 and 32. Does not work. If n is equal to 4, we have 216, and then we have whatever 4 times. It's really 128. Yeah. So, okay. So then, okay, wait, did I do that right? 2 to the 8. Oh, I did do that wrong. Okay, so you have 2 to the 8 minus 1 is not that. And this is also not 32. This would be, oh wait, yeah, I completely butchered that math. I thought it was 2 to the 2n minus 1. Oh wait, yeah, that was wrong. It's 2 to the 2n minus 1. Okay, if n is 3, then, wait, this changes a lot of things. Okay, if n is equal to 3, then 6 to the n minus 1 is still 36. Then we have 2 to the 6 is 64. So this is 63. So this checks out. If n is equal to 4, then it would be 2 to the 8, which is 1024 over 4. So 256. So the whole thing would be 255. This also works, but I have a very strong suspicion that this grows faster than this. So I'm assuming that for n is greater than or equal to 5, that would be wrong. So now, if n equals 4, what does this mean? This means that our base 6 has 4 digits. Our base 2 has 8 digits. And we need to find what? What is the problem state? We need to find the greatest positive integer. So we're just trying to maximize one of these two bases. I think that if we maximize the base 2, it should work because, well, let's see. Yeah, because, oh yeah, the reason that you need to find, okay, so you either have two choices. Either maximize the base 6, which is 1, 1, 1, 1 base 6, and then convert that to base 10, or you have 1, 1, 1, 1, 1, 1, 1, 1 in base 2 and convert that to base 10. Okay, 1, 1, 1 base 6 is probably greater than base 2 because base 2 numbers have their digits grow faster. So we're using that reasoning. We're basically just trying to convert this one. So this, it would probably be like 9 digits in base 2. So yeah. So that's why we're trying to now just solve for this. So a nice trick is if we add 1 to both sides, plus 1, we have x in the base 10 plus 1, and then that plus 1 literally rolls everything over. So now we have 1 followed by 8 zeros. So this is just 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is just 2 to the 8 is equal to x to the 10 plus 1. So 2 to the 8 minus 1 is equal to x. 2 to the 8 is 256, minus 1 is 255 for the answer. All right. Last one is, this one is interesting because it low-key requires like a thing that, it's like a hint, not a hint, like a trick that you would see a lot in AMC or something like that. But actually, this pattern is used a lot, and the nice thing about it is when you have this pattern, it'll always start to repeat given any input, right? So say if I put in a number n, and I just do this process where I take the ascending digits and minus the descending digits, right? Or the other way around, but you know what I'm saying. You do that, it'll always reach a constant value. And the nice thing is that we're trying to find any. So we don't like need to find any. We don't need to find like any like certain one. We just need to like literally plug in a number and it'll literally work, right? For example, like what I mean by this is that if we literally just take in 1, 2, 3, 4, the reason you're doing 1, 2, 3, 4 is because the numbers are not, I mean, it would work with any, like even if you did 1, 1, 1, 1, it would work. Or well, you have to have the digits at least somewhat different because if you did 1, 1, 1, 1, it would just be 0. But if you do 1,234, and then do 4, 3, 2, 1 and subtract that in base 5, you'll find a pattern. And so right here, let's just subtract these two numbers. This would be 6. This would be 6 as well, and this would be 2. So 3, 0, 3, 2, right? This is a number we get. Now let's do the pattern again. Do 3, 3, 2, 0, 0, 2, 3, 3. This would be 5. This would be 6. This would be 2. And yeah, that would be okay. So we have 2, 3, 0. Wow, that's cool. We always get that number. The reason we got this number in the first place was we just randomly applied the pattern. There's nothing special. There's nothing special at all about the numbers. You can take any numbers and just like play with it and find out it works. So this is a tactic. I don't think you guys will need to see another problem like this at NSML. But if you ever see a problem like where it's like this pattern, literally any input will like get you a like actual answer, right? It'll get you like, for this case it converges immediately, but for other cases like it might take like 3 or 4 patterns, but you'll eventually reach like a constant number where when you input that constant number again, you'll get that number back. So yeah, that's pretty much it. The answer is just 3032. We just showed that it worked. So yeah, it was a nice problem. If you got it, good work. That was pretty cool. So yeah.